Welcome everyone to the class. This will be our last class for this subject. From the last couple of classes, we are studying problems. Dedicatedly, these sessions we kept in order to solve problems which are asked in previous year for all these chapters. Um, Till now, we have studied the problems on mechanics and machines, velocity and acceleration, dynamics of linkages, gears and gear trains. Um, Camps also we have studied what kind of problems they'll ask. Some questions we have solved from I guess governors also. Okay, so in today's session, our focus on solving the question from the flywheels. Okay, and the gyroscope. Okay, but before we jump into that, one question was remained from the last class, which we were studying, and um, there was some connection issue. So I'll take that first, and then we'll start with the question from the remaining topic. Okay, can we proceed? Yes. Okay. So let's take this question. As I said previously, a slider crank mechanism with a crank radius is okay, with a crank radius 60 millimeter, and the connecting rod length is 240 millimeter is shown in the figure, and the crank is rotating with a uniform angular velocity of 10 radian per second. The question is that too with a counterclockwise direction. Question is, for the given configuration, the speed of the slider is okay. Slider speed they have asked. Okay. Okay. So this is 60 and 240. Okay, and this is the situation, 10 radian per second. Okay, I think we'll directly jump to the solution because some time we have spent on it in the last class. So I have already prepared a solution for it, so that it will be very fast and we can move forward. So as I said, 60 millimeter is our crank length, 240 millimeter is our um, length of the connecting rod, and they are asking us VS. Okay, so if the velocity of the slider, what it will be? VS is the velocity of the slider. If you take cos component of the velocity of slider, um, so that will be like V, right? So that should be this V. Okay, so Vs cos of theta is equal to V. So Vs can be written as V divided by cos of theta. So ultimately in this question, you should be able to find first of all V, okay, this V, and you should be able to find theta. These are the main tasks which you should know, because by this rule we should be able to find the velocity of slider. Okay, so how will you find the theta? As we have already studied, this angle has to be 90 degree in order to achieve it. Okay, uh, because in the in the diagram itself they have given this as a 90 degree. Okay, fine. So coming to the question, you can use the Pythagoras theorem, and diagonal square is equal to height square plus base square. You will get is as diagonal around 247. Okay, and you can find the V. V is equal to R omega. So by this R is 60 millimeter, so it is 60 divided by 1000 multiply by 10, you will get 0.6 meters per second. This is your V. So you got V. How will you get theta? Take anything like tan of, or you want cos of theta. So cos of theta is equal to what? Base divided by hypotenuse. Base here is 240. Okay, and hypotenuse here is this 240. 247.38, which we calculated. 297, sorry, this is 297. Okay, 297. And with that, you will end up with the um, velocity of the slider as this. Okay, so let me just confirm. Let me just calculate whether this is 247 or 297. 240 into 240 plus 60 into 60. Okay, rest to the power 1 by 2 or 247 itself. Yeah, not 97. 247 is the correct. So this is a typo here. Make it 247.386. Okay, yes, correct. So this is how you can calculate. Otherwise, you can draw the velocity triangle and all. From that also you'll get the answer. But this is one of the simplest method which you can use, and yeah, in order to solve these type of questions. Okay, can we proceed to the next slide? Yeah. Okay, so now we'll focus on mainly the rest of the topics: flywheels, governors, and gyroscope. Just to recall the definition, what is the difference between, let's focus on flywheel and governor first. What is the difference between flywheel and governor? Flywheel is used to control the or maintain the speed. Okay, maintain the speed of the engine. Yes, in each cycle basically. Okay, um, in each cycle, whereas like governor is like depending on different kind of loading. Okay, yeah. So yeah, it's intermittent, you can say. Whenever loading is varying, our speed will vary, and in order to control our speed during that time, we use governor. Okay, so governor is to again used to maintain the speed, but under the different loading, whereas flywheel is used for as you said, it's a continuous loading. um, in case of continuous loading, but uh, in each cycle we know, like, there will not be a power stroke at every moment. So first, let's say if you take a single um, cylinder engine, in that case you will have suction stroke, compression stroke, and then power stroke, and then exhaust stroke. So you'll have, out of 4 strokes, there is only 1 stroke where you will get the power. Rest of the 3 strokes, you need energy, basically you need power. Okay, so in that case, flywheel store the power during power strokes and give that energy or give that power during the other strokes. Okay, so that is why it is continuously working, storing the energy, giving the energy in each cycle. Okay, whereas the governor is like, it will not work for each cycle. So for example, load is constant on the engine will work at a constant velocity or constant speed, sorry. And as you um, change the loading, the engine speed will likely to change, and in order to maintain that, what we are doing is we are using governor there. Okay, so this is the basic background behind it. Let's come to the questions now. First question we have is, a flywheel of moment of inertia I is equal to 9.8 kg meter square, fluctuates by 30 rpm. Okay, for a fluctuation in energy of 1936 joules, the mean speed of the flywheel is in rpm. Okay, I will repeat the question. They have given us the value of y, 9.8 kg meter square. Delta omega is 30 rpm. In rpm they have given. Okay, so it's a not in the radians per second. Okay, it's in rpm, remember. The fluctuation in energy delta E is also given to you, 1936 joules. Mean omega they are asking. Okay, in rpm. Okay, so can you try to solve it? If you remember the formula, I will just write the basic formula from the flywheel here. delta E is equal to I omega delta omega. How we have calculated this? Half of I omega 1 square minus omega 2 square. Okay, and I by 2, a square minus b square is a plus b and a minus b. So this is your delta omega, and if you write 2 here, this is your mean wind speed. So I omega delta omega. Okay, so this is how this formula is calculated, that is changing the kinetic energy. Okay, um, or energy stored in the flywheel is calculated by this formula. So basically, as I said, delta E is I omega delta omega. Okay, so use this formula and try to solve this question. You have everything here. Delta E is given to you 1963. I is also given to you 9.8. Omega is you are supposed to calculate omega mean because it's mean um, value, so it's written by omega, and delta omega you already know, which is 30, but it is in rpm, so it's a 2 pi n divided by 60. Okay, so that you will have all the terms in SI unit, and then you can cancel out them, and you should be able to get the value of omega. So this 2 will get cancelled, 60 will get cancelled. Omega is equal to 1936 divided by 9.8 into pi. Okay, so think it should you should get it around 62.88 radian per second, but they want in rpm. So again, this is equal to 2 pi n divided by 60. So 62 into 60 divided by 2 pi, you should end up with I think 600 rpm. Okay, so option A is correct in this case. So these kind of questions you can expect for 2 marks. um, okay, it's not that difficult. As I said, in flywheel there is no um, not much variety they can ask. Okay, so write it down and I'll proceed to the next slide. Okay, I'll go to the next slide. So read these following statements and tell which of the following statement is correct. Okay, so first statement, flywheel reduces the speed fluctuation during a cycle for a constant load, but flywheel does not control the mean speed of the engine if load changes. Okay, this is the first statement. Second statement, flywheel does not reduce the speed fluctuation during a cycle for a constant load, but flywheel does change the mean speed of the engine if load changes. And third is, governor control the speed fluctuation during a cycle for a constant load, but governor does not control the mean speed of the engine if load changes. So yeah, you can clearly see a lot of questions. Uh, um, so first of all, this is wrong statement. We know governor controls the speed fluctuation um, if the load changes, right? If the load changes, governor changes the speed fluctuation. So this is wrong. Even option B is wrong. Why? Because flywheel does not reduce the speed fluctuation during cycle for a constant load. So this is wrong statement. It does actually, right? Do you agree? Yeah. So, and what is the last option? Governor controls the speed fluctuation during a cycle for a constant load, and governor also controls the mean fluctuation of the engine if load changes. So this is quite wrong. Second statement is correct here, but this is wrong. It is not controlling um, the speed fluctuation during each cycle. So option A is correct. Okay, so this kind of theoretical questions also, you know, this question for a certain engine having an average speed of 1200 rpm. So what is this? Can you tell me what is this? Omega, right? Omega is given to you. Omega is 1200 rpm. Yes. The fly approximated as a solid disk and speed 2%. Speed is 1200 rpm and delta omega is 2% of this. Just a minute. Uh, just give me a minute. How about now? Can you hear me properly? Yes. Okay. Good. So the fluctuation in the kinetic energy per cycle is also given to you. That is delta E. What is the least possible mass of the flywheel if its diameter is not to exceed 1 meter? So diameter maximum limit is 1 meter. Um, what is the mass? That is what they are asking to you. So it's a solid disk. Okay, solid disk means mr square by 2 is your moment of inertia. Okay, that is hint to you. I is equal to mr square by 2. This is what you can use here. All other things are known to you. You should be able to solve this question. Delta E formula you already know. I omega delta omega. Okay. If in this case, if I multiply and divide by omega, this formula will become I omega square into delta omega by omega. And this will become I omega square CS. Okay. CS is fluctuation in the speed basically here. Okay. And what is the value of I? M R square by 2 into omega into CS. This is your delta E. So from this, I should be able to write M, which is equal to 2 delta E divided by R square into omega square into CS. Okay. So you already know the formula. Now I expect the solution from you. So 2 into delta is what? Change in the uh, kinetic energy, that is 2 kilojoules. So it's a 2000 joules, right? 2 into 2000. Diameter is 1. So radius is 1 by 2, that is r square, into omega is 1200 rpm. So 1200 omega is equal to 2 pi n divided by 60. So it is 2 pi. N is how much? 1200 divided by 60, 20. So it's a 40 pi, which is 125.66 radian per second. So it's a 125.66 whole square into CS. CS is what? CS is 2% they have given, 0.02. Delta omega by change in omega with respect to the mean wind speed is 2%. So that is 0.02. And this will directly give you the mass, which is 50.66. So approximately 51 kgs. Okay. So option B is correct in this case. Are you following it? Can I proceed to the next slide? Yeah. Okay. So take this question. This is also very simple question from 2006 gate. If CF, or sorry, what is that? CF, yes. CF is a coefficient of speed fluctuation of the flywheel. Coefficient of the speed fluctuation means delta omega by omega. Okay, this is your CF. Then the ratio of omega max to the omega minimum will be. Okay, this is the question. I'll give you 2 minutes to solve. If you are unable to find the answer, then I'll help you. See, let me check it. No, D is the correct option in this case. Okay, I'll help you. It's not that difficult. See, the hint here is CF, is what? CF is equal to delta omega by omega, as I said. What is delta omega? Omega max minus omega minimum divided by delta omega means omega max plus omega minimum divided by 2. Okay. So what you can say in other words, like if this 2 you can take in the numerator and do the cross multiplication. Can I write like this CF into omega max plus plus CF into omega minimum equal to 2 times omega max minus omega minimum, right? We can write it like this. And then maybe you can, let's say, you want omega max by omega minimum, so divide everything with omega minimum. Okay, omega minimum, omega minimum, omega minimum. So this will get cancelled. Omega by omega max by omega minimum will remain here, and here also you have the same. So take it on the left hand side. Here also 2 will come, and you can just solve it. Okay, it's not that difficult. So I will say 2 minus CF times omega max by omega minimum is equal to, on the left hand side, what will come? 2 plus CF will come, right? So this implies omega max by omega minimum will be equal to 2 plus CF divided by 2 minus CF. Are you getting it? Yeah, it's just the simplification. Okay, I'll go to the next slide. The speed of the engine varies from 210 radian per second to 190 radian per second. Okay, so omega 1 is given to you 210, omega 2 is 190. Okay, during the cycle, the change in kinetic energy is found to be 4 Newton meter. Okay, the question is the inertia of the flywheel in kg meter square. It's, they're asking about the I. But it's very simple. I'll give you 2 minutes of time to solve. If you are finding it difficult, then I'll help you. Okay, option A. Let me check the answer for this. Yes, option A is correct. 0.1. Yeah, I'll just help you with this. Delta E, as we know, is half of I omega 1 square minus omega 2 square. Yeah, delta E is given to you 400, which is equal to half of I. Omega 1 is 210 square minus 190 square. That's all. So if you solve it, you should get I is equal to 0.1. Okay. Coming towards next question. A flywheel connected to a punching machine. Okay. Okay. Question is quite different here. You have a flywheel which is connected to the punching machine, has to supply energy of 400 Newton meter while running at a mean angular velocity of or mean angular speed of 20 radian per second. If the total fluctuation in the speed is not to exceed plus or minus 2%, okay, the mass moment of inertia of the flywheel is, okay, this is what they are asking. Delta E also how much? E is E they have given. It's not a 400 Newton meter. Yeah, delta E you can say. Delta E is equal to 400 Newton meter. Omega is equal to 20. Delta omega is plus or minus 2%. So they have given like total 4% variation is allowed in the speed. So I can write it as 0.04, the value of delta omega by omega. Okay, so it's basically CS they have given 0.04. Now they are asking. You already know the value. Delta is equal to I omega square CS. Okay, so it's not a difficult question. Delta is 400. I omega is 20 square. CS is 0.04. What is the value of I? It's 25. Okay, option A is correct in this case. Yes. Okay, I'll go to the next question. See, you can clearly see there is no other way to ask questions on the flywheels. Flywheel is one of the major topic from Tom. Okay, in theory of machines, if you see the previous year paper, majority of the questions are coming from let's say the three topics. Um, I'll consider this velocity acceleration, mechanics and mechanism and dynamics as one topic itself. So all these three topics, if you combine, either you'll get from that, or gear and gear trains is also we can combine together. From that we'll get one question, and the flywheel. So these three are major um, contributors for questions, you can say. Okay, so if you see the previous year question, you will see mainly the questions are asked from these three main sections. You will rarely find questions on, let's say, gyroscope or cams. Okay, but for cams we have studied. Gyroscope also will study some question, but that's the reality. Okay, but I would not suggest you to keep anything for option. You should study all the topics, but give more emphasis on these three topics. Okay, so let's study this next question. Maximum fluctuation of the kinetic energy in an engine has been calculated to be 2600 joules. So delta E is given to you. Assuming that engine runs at an average speed of 200 rpm, omega is given to you. The polar mass moment of inertia in kg meter square of a flywheel to keep the speed fluctuation within plus or minus 0.5%. So it's a clearly del CS is how much? Can you tell me now? What is the value of CS? Yes, it is 0.01. Correct. So now you got idea about it. 0.01 you can say of the speed. So what they are asking is polar moment of inertia. So solve this question. Delta is given. Omega is given in RPM. So 2 pi n divided by 60 if you do. How much? 2 pi into 200 divided by 60. 20.93 you will get radian per second. Okay. So you got omega. I you are supposed to calculate delta E is equal to I omega square CS. I is equal to delta I divided by omega square, so omega square into CS. Delta I is known to you, 2600. Okay, 6.5 is not correct answer. Sean, check it again. Omega square you have to do 20.93 whole square into CS is 0.01. I would expect around 593.33 kg per meter square. Okay. See, because the square of this is 400. Around 400. Okay. Yes, 593 is the correct answer. Okay. I'll go to the next slide. The this is little different question. Okay, this is little different question. So I'll just read this question first. The torque in Newton meter exerted on a crankshaft of a two-stroke engine can be described as. So torque, for torque they have a relation which is 10 to thousand feet. Okay, this is the relation given to you, where theta is the crank angle as measured from the inner center position. Okay, assuming the resisting torque to be constant, the power in kilowatt developed by the engine at 100 rpm is. So they are asking you to calculate the power. What is power torque relationship? P is equal to 2 pi n T torque. 2 pi 60, right? Torque. Okay. Solve this question. I'll wait more minutes. My voice is breaking, it seems. Okay. Yeah. I'll try to resolve the issue. In the meantime, how about now? Is it clear? Yeah, okay. Solve this question. Problem is here they have not given you the torque directly, mean torque. They have given an expression, but they have clearly mentioned it's a two-stroke engine, and the torque is varying in this fashion. So ultimately here you somehow you have to calculate the mean torque. This is your mean target. This is your first target, and once you calculate it, you can put into this formula and get the solution. Okay, I'll help you with that. So theta is a crank angle, and you can clearly see that theta will vary from 0 to 2 pi. In a two-stroke engine, in a single revolution itself, all the strokes are done. Okay, so 0 to 2 pi is your angle, okay, of crank rotation, and in that, if you integrate it, so 1 upon 2 pi integration 0 to 2 pi will give you the mean value of torque. Okay, so you integrate it, integration of 10,000 is 10,000 theta plus 1,000 as it is, integration of sine of 2 theta is mm, minus cos of theta divided by 2 minus 1200 as it is, integration of cos of theta is sine of 2 theta divided by 2, and then if you uh, put the limit 0 to 2 pi, ultimately you'll end up with this value 10,000. Okay, so I have directly written it. You can solve it and solve this integration and check. 10,000 is what you should get, and once you put this 10,000 into this formula, you will get around 105. Okay, so the power in this case is power developed by the engine is 105 kilowatt. Okay, yeah, if it is a four-stroke engine, what will happen? First stroke. So let me just try to help you with the figure. Let's say this is top dead center, bottom dead center, and let's say piston is initially here, connecting rod. Let's say piston is somewhere here. Okay, and this is a crankshaft. So imagine like first stroke is compression. Then basically in compression stroke, our crank rotates by 180 degree. Then second stroke is the piston will come down, um, or let's write it other way around. First start with the suction stroke. It will piston will come down, right? Okay, let's take it counterclockwise. Piston will come down. Then the next stroke is compression stroke. Piston will go up. Okay, um, and then expansion stroke, and rather, or you can say power stroke, and then we have exhaust stroke. So here it is 180 degree, here it's 180 degree, here it's 180 degree, here it's 180 degree. So it's 180 means pi, it's a 4 pi. So 0 to 4 pi will be your integration if it is a four-stroke engine. In two-stroke engine, it's only uh, let's say one full cycle. Okay, can I proceed? Okay, so we are almost done with the questions from governors and flywheels. Let me bring some questions from the gyroscope. Mm, I'll take these questions from SS Ratan book. Okay, I was not able to find much questions on this from previous year papers, but we do have some questions from SS Ratan. We'll take it. Yeah. So here the main formula, if you remember previously, What is the formula for gyroscopic couple basically? Can you tell me? I omega, yeah, I omega omega p, right? I omega omega p, we can say. Okay, so mainly the questions will be like they can ask only on this topic. Otherwise, the rest of the question will be theoretical, which you should be able to solve it, because we have studied like how the gyroscopic effect will affect on two-wheeler or four-wheeler or aeroplane or ships. Okay, so it should not mm, be difficult. Let's take a question. A uniform disk having a mass 8 kg and a radius of gyration of 150 mm is mounted on one end of a horizontal arm. Okay, one end of horizontal arm of 200 millimeter length. The other end of the arm can rotate freely. Other end of the arm can rotate freely in a universal bearing. Full stop. Determine the motion of the disk. Determine the motion of the disk. If the arm remains horizontal. Okay, solve this question. So they have given a disk of mass which is equal to 8 kg. The radius of gyration is given to you, that is k is 150 millimeter. That is mounted on one end of the horizontal arm. The arm length is also given, which is 0.2 meters. Okay, which can rotate freely in a universal bearing. Determine the motion of the disk if arm remains horizontal. I think one thing I have missed to write. The disk is given a clockwise. Okay, after bearing. Here I have one point which is remain. Disk is given a clockwise spin of disk. Here one statement I forgot to write. Disk is given a clockwise spin of 250 rpm from the disc end of the arm. From the disc end of the arm. Okay. So take this question and so n is also given to you. N is 240 rpm. Okay, correct it. 240 rpm. So for example, we have I is equal to what? Moment of inertia is I is equal to mk square. 8 into 0.15 square, because 150 millimeter means 0.15 meter. It will give you 0.18 kg meter square as your moment of inertia. Omega is 250 rpm, convert into radian per second. 2 pi into 240 divided by 60. It will be around it's 8 pi 25.13 you should get radian per second. Okay, so you got I, you got omega. Omega p is not known, but think on this question, what they are asking you. So you have a uniform disk having, so like this you have a disk, right? And yeah, this disk is connected at one end of the uh, horizontal arm, which is 200 millimeter in length, and other end of the arm can rotate freely in a universal bearing. So this is, here you have bearing, fine. Here you have given a rotation of a clockwise 240 rpm, right? This is what they have. So basically, what are the forces you can expect here? The one force I will expect is this mg force will acting on downwards. It will create a moment about this bearing, which is mg into L. And this mg into L, because of the self weight, it will create a gyroscopic effect. Okay, so it's just rotating at 240 rpm, fine, but it is overhang, and because of that, like, it's same as applying downward force because of its mass, and it will create a gyroscopic effect here. So because of that, the gyroscopic couple formed here should be equal to the moment generated about this bearing. So I can say that mg into L has to be equal to I omega delta omega. Okay, sorry, I omega omega p. I can say it like this. Okay, as the disk is rotating, weight of the disk acts as a downward force, you can say here, and thus um, a couple about y-axis in the clockwise direction is applied on the disk. So maybe I will um, yeah, 3.47 is the correct answer here, Sean. That is, let me, I'll go to the next slide. As I said here, mgl is equal to I omega omega p. M is 8, G is 9.81, L is 0.2, I is 0.18, omega is 25.13, and omega p, if you calculate omega p, as you said, Sean, you'll get 3.47 radian per second. So but at the same time, you should know like practically what's happening here. So this is your x-axis, this is y-axis, and this z-axis, for example. Okay, and we are giving a clockwise motion here. So considering right hand thumb rule, um, no, I will show you what will happen. Uh, can I say this vector A will represent um, uh, the motion? Yes, right, because it's from here we are rotating it clockwise, so the arrow is in left direction. And now what we are doing is, because of self weight, this will come down. So it's like um, the vector B here. Okay, assume that axis of the spin is OX. Okay, um, and uh, the vector OA would rotate to the position OB in the short period, you can say. Then AB is, you can say, an applied couple here. AB is an applied couple. So here this will be your gyroscopic couple B dash A dash. B dash A dash is a reaction couple, and which is clockwise, because you can clearly see this. Use the right hand thumb rule. It is a clockwise here, not a counterclockwise. It's a clockwise, and tends to give the arm clockwise rotation about the y-axis. So try to imagine. So it will try to give a clockwise motion about the y-axis. Okay, so this is what happening here. Uh, yeah. So I'll go to the next slide and try to give you one more question. Just give me some time. Yeah. Yeah. Okay. We have one more question. Okay, a little big question. I will write. An aeroplane flying at 240 kilometer per hour turns towards the left and completes a quarter circle of 60-meter radius. Full stop. The masses of rotary engine and the propeller of the plane is 450 kg with a radius of gyration of 320 millimeter, full stop. The engine speed is 2000 rpm clockwise when viewed from the rear. Determine the gyroscopic couple okay. Determine the gyroscopic couple on the aircraft and state its effect. Okay, just a theoretical question. It's like not from gate perspective, but at least they can ask you to calculate the gyroscopic effect. Okay, they'll not ask you to state it, but you should be aware of it theoretically what's happening. So at least formulation you can expect in gate, but they'll not ask you to write anything there, but you should be able to visualize it, understand what's happening. Determine the gyroscopic couple on the aircraft and state its effect. Sorry, one the other part here is in what way the effect change when the effect changed when the first one is aeroplane turns towards right, turns towards right, and this another second question is engine rotates in clockwise when viewed from the front nose, from the nose, which is front end. Okay, and the aeroplane and the aeroplane turns here in sub part we have left and another sub part is right. So we have like almost three questions here. Okay, quite big question. I'll explain once again what is given and what is expected here. The aeroplane is flying at 240 kilometer per hour. So uh, they have given the speed of the aeroplane here. So velocity is given 240 kilometer per hour. Okay, so 240 into 1000 divided by 3600 will give you the velocity in meters per second. 240 into 1000 divided by 3600 or 5 by 18 if you do the same thing, 66.67 meters per second. So this is first thing given to you. Okay, apart from that, so what it will help you? It will help you to calculate the omega p, because omega p is equal to v by r. We know. It takes okay, it turns towards the left and completes a quarter circle of 60-meter radius. So radius is also given to you. Velocity we have just calculated, so omega p you should be able to calculate 66.67 divided by 60. It is 1.11 radian per second. Okay, so this first part is clear. The masses of rotary engine and the propeller of the plane is 450 kg with a radius of gyration 320. So m they have given is 450 kg, Radius of gyration they have given 320 millimeter. So I is equal to mk square. M is 450. K is 0.32 because it's in meter. You have to calculate. You should get the value of I. I is equal to mk square. I'll go to the next slide. I is equal to mk square. M is 450. K is 32 by 1000. Sorry, it's a 320 by 1000, which is 0.32 whole square. I will end up with 46.08. Correct, kg meter square. So this is the second part here. The engine speed is 2000 rpm clockwise when viewed from the rear. Omega they have given. Omega they have given 2000 rpm. So 2 pi into 2000 divided by 60. So nothing is given directly. You are supposed to calculate all the things. So it will be around 209.4 radian per second. Okay. So I hope it's clear now. They have given indirectly given you the I, indirectly given you the omega, indirectly given you the omega p. You are supposed to calculate it by using given things. The engine speed is 2000 rpm clockwise when viewed from the rear end. Determine the gyroscopic couple on the aircraft and state its effect. Okay. So let me just try to draw an aeroplane. Okay, so for example, this is the aeroplane, and the engine speed is 2000 rpm clockwise when viewed from the rear. So for example, it's rotating in clockwise direction. Sorry. And as we have seen, it turns towards left and it's taking a left turn, right? This is what we have studied in the in the beginning. So if you see what is happening, um, if it takes a left turn, so first of all, mm, how you will draw the diagram? Yeah. So this is, for example, OA is your initial velocity vector. Do you agree with this? The effect of gyroscopic couple we are trying to draw first. When it takes a left turn, um, I would expect it to become like this. So it's a O2A and O2B I will write here. So AB here is OA is angular momentum vector before turning. OB is angular momentum vector after turning to left side, and AB is active gyroscopic couple. So BA is an reactive gyroscopic couple, or let's say B dash A dash is a reactive gyroscopic couple. So if it is coming down, it's a counterclockwise. So what will happen because of this? It will tend to rise the nose. Yes, no, nose will not go down, Sean. You can imagine it's like moment here, nose will come up and bow will come, the rear tail will go down, tail will go down. Okay. So depress the tail and rise the nose you can expect here. And what is the value of the couple here? C is equal to I omega P. I is already calculated for 46.08 into 209.4, which is omega P is 1.11, so it is 10.713 kilonewton meter. Okay. Yeah. Okay. Um, no problem, Sean. So next question here: aeroplane turns towards right. What will happen? Turn towards right. This is the vector OA. This is the OB vector. Active gyroscopic couple, reactive gyroscopic couple, and clockwise will be our um, reactive gyroscopic. Uh, that is the gyroscopic effect basically. So when the engine rotates, spin clockwise, but takes a right turn, what's going to happen is it will dip. It will uh, nose will get depressed. We can say yes. Nose will go down here in this case, as it's a clockwise reaction. Nose will come down and tail will go up. Okay. So correct, you are correct. Nose will go down in this case. And the third question is what? Engine rotates in clockwise when viewed from the nose side. So basically now engine is previous from here it's a clockwise, means from rear it's a counterclockwise. Okay, from rear it's a counterclockwise. Fine. Um, so whatever we have discussed before, just the opposite of it will happen. Okay. If you want, I will explain. Let's say um, the arrow will come in this direction, O to A, right? O to A will um, yes, O to A will, or let's say call it as O to E will come now. And then let's say if it takes first left turn, um, yeah, if it takes left turn, EF I will say. EF is active gyroscopic couple, and F dash E dash is a reactive gyroscopic couple, and here it will be clockwise. So it will be like nose will go down. Yes, perfect. And if it takes a right turn, OE, OF clockwise. Now here in this case it's a counterclockwise. Here nose will go up. Okay. Yeah, that's all. Um, if it takes a right turn. So I hope, yeah, you understood here how things will change when we are considering the motion in opposite direction. Yeah. So same thing is there in ships. So uh, we'll not discuss much about it. Let me just take another one question from balancing. Okay, one question from balancing I'll take. This is also from SS Ratan. We have, I think in the last class we have solved two questions from balancing. We'll take one more. This is from SS Ratan. A circular disc mounted on a shaft carries three attached masses of 4 kg, 3 kg, and 2.5 kg at a at radial distances of 75 millimeter, 85 millimeter, 50 millimeter, and at an angular position of 45 degree, 135 degree, and 240 degree respectively. Okay, full stop. The angular positions are measured the angular positions are measured counterclockwise counterclockwise from the reference line along the x-axis determine the amount of counter mass at a radial distance 75 mm required for the static balance. Okay. Um, so basically, I'll just give you rough figure of it to understand your situation here. So we have one mass which is of 3 kg, which is at an angle of 45 degree. 45 degree. We have mass of 4 kgs. Then we have 3 kgs at a 135. This angle is 45, 135. Here it is 3 kg, and then we have 240, 240, and it is 2.5. Okay, so this is the situation, and their radial distances are also given. This is at 75 mm from the center. This is at 85 mm from the center. This is at 50 mm from the center. Okay, the angular um, the angular positions are measured counterclockwise from the reference line. Yeah, we have also done the same um, along the x-axis. Determine the amount of counter mass at a radial distance 75. So I'm drawing just a randomly. I don't know. Okay. So for example, you in order to balance it, you can clearly see it's not balanced. In order to balance it at certain distance of let's say 75 mm, they have mentioned here 75 mm. How much mass MC you have to attach? Okay, and what should be the value of theta c? Okay, determine the amount of counterness at a radial distance 75 required for a static balance. So first you should MC itself they are asking, but I also want you to calculate not just um, MC but also theta c. Yeah. So if you remember what I have taught you, um, m1 r1 omega square plus m2 r2 omega square plus m3 r3 omega square plus counter mass into that radius into omega square will be equal to 0. Okay, everything is rotating with omega. So if you cancel out omega, m1 r1 plus m2 r2 plus m3 r3 plus mc rc has to be equal to 0. These things are known to you, m1 r1 m2 r3 mt r3. So summation of all mrs plus mc rc has to be equal to 0, right? Then only we'll say we have made the system statically balanced by attaching a mass mc at a radius rc. Okay, and then it's your task to how to calculate this mc and rc. You know, you have to take the cos components of it and sine components of it. What you can do is summation of mr cos of theta plus mcrc cos of theta c
You are
will give
currently
you,
the only person in this conference.
okay, will give you 0 answer. Similarly, summation of mr sine of theta plus mcrc sine of theta c equal to 0. So these two equations you have to solve in order to get the values of um, mc theta c. Rc is already given to you, so that's not an issue. So for from this I can write mcrc cos of theta c equal to minus summation mr cos of theta and mcrc sine of theta c is equal to minus summation mr sine of theta. If I so you solve these two questions, you will get the value of um, basically uh, mc and theta c because rc is known to you. If you take a ratio of it, simply mcrc will get cancelled. Tan of theta c, what you can write is equal to minus minus will get cancelled. Summation mr sine of theta divided by summation mr cos of theta. So this is also an good formula to calculate tan theta c. Okay, so use these approaches to solve this question. And if you add also these two, so this is, let's say, equation number 1 and equation number 2. Equation number 1 square plus equation number 2 square is what? Sin square theta plus cos square theta will become 1, and ultimately this formula will become mcrc will be equal to, okay, I'll go to the next slide. mcrc will be equal to under root of summation of mr cos of theta whole square plus summation of mr sin of theta whole square. Okay, yeah. So in this way also you can, rc is known to you, that is 75. You should be able to solve it. Okay, mc, you are saying no, mc is wrong. You should get it as 3.81 kgs. Take it once again, Sean. Is it correct? mc into 75 is equal to under root of, let's say, summation mr cos theta. So what is m1? 300. Why 300? Because first mass is 4 kg and it is at a 75 kg, 75 mm. So 4 into 75 is 300. Yes. So 300 cos of 45. Okay. Plus next one is the mass of 3 kgs at a radius 85. So 3 into 85, 255 cos of 135 plus next one is mass of 2.5 kgs at 50, so 2.5 into 50, 125, cos of 240. So this whole square plus sine terms will also come in this under root. 300 sine of 45 plus 255 sine of 135 plus 125 sine of 240 whole square. If you solve this, what we'll get is under root of minus 30.68 whole square plus 284.2 whole square. Okay, so it's 285.8 kg millimeter you will get, and that is equal to mc into 75. So indirectly mc is equal to 3.81 kgs you should get. Check it once again. It's not that difficult. And theta c, as I said, you will again implement the formula. So what was the formula? Summation mr sine of theta divided by summation mr cos of theta. Just now we have written the terms. Summation mr sine of theta was 284.2 and summation mr cos of theta is minus 30.68. Okay, so if you solve it, tan of theta c, so it was minus minus, so it will become minus 9.26. So theta c will be equal to tan inverse of minus 9.26, and that is equal to 276 degrees and 12 minutes. Okay, and it will lie in the fourth quadrant because it's more than 275 degrees. Sorry, more than 270 degrees. So as I have already drawn in this figure, it's more or less correct representation of it. Okay, is it clear to you? Any doubt in these questions? Okay, so more or less we have covered all the topics here. I tried to give a glimpse of the uh, previous year questions which are asked in all these topics. I hope you at least got some idea what kind of questions you can expect in exam from these topics. Okay, I would suggest you to revise it once again, whatever I have taught you. I will maybe by tomorrow I will put all the material in the one in a Google Drive location. Okay, and sir will share that with you. I have received a location where I'll upload the this problem solving session slides and the slides from the theoretical part which we have studied. Okay, and you also have the recordings, so both are there. You go through it once again, try to solve uh, try to go through these all questions and then go to the previous year questions. Okay, and if you still find any difficulty in conceptual or in let's say any of the part, feel free to reach out to me. Okay, I hope you already have my number. If it is not, I will give you again. Yeah, I will. I'm just putting my number in our chat group. Okay, you can message me on WhatsApp if you find any problem difficult and need some guidance. You can reach out to me, or if you have any conceptual doubt also, feel free to ask. Okay, but I expect from you that you should just first go through this all the topics which you have studied on your own first. Okay, I have taught you all of them. It's your duty to revise it once, and once you have done the proper revision and then start solving questions on your own. Okay, we have studied most of the questions, like from each topic we have studied a lot of questions, but as many as questions you solve, you will get more familiar, will get more familiar with it, and in exam you will be easily able to solve those. Okay, so I would suggest you again to go through this entire syllabus, through the recordings or slides, and start solving the questions on your own. Okay, so with that, I think we should stop here now. We are at um, we'll close early today, and yeah, thank you all for joining this session, and let's be in touch in case of any doubts. Okay, okay, then thank you, bye, and have a good weekend.
You are currently the only person in this conference.